Alright everybody, hello and welcome to another one of these Geometry of Pattern episodes series. Today it is Thursday, January 21st, 2021, and it's a beautiful cloudy day, man. A lot of smog and fog. It's a beautiful day. On the board over here we have written a quote from a book called Island by Aldous Huxley. It says, "It is dark because you are trying too hard. Lightly, child, lightly. Learn to do everything lightly." And well, the quote isn't complete, but it's a beautiful quote, I think. And today, well, we're going to look at star polygons, and we're going to look at the minimal triangle approach. Well, we're going to look at more to do with the minimal triangle formula, something that I've kind of like come up with, and I think it's useful to try and like generalize certain things, and it helps with understanding sometimes how things might click together that are similar or have something in common. So it's a great thing to try, and it has come to my attention that children watch this, so I will not cuss, I will like, so I won't even mention it no more. So we'll look at some fun math, we're going to try and do that. And we're going to smile more. And we're going to see how where that takes us. Alright, so let's just jump right into it. So, alright. Well, alright, so this friend of mine, Sufyan, at Geometry on Instagram, you want to check him out, he's there. But he asked me, like, he's a mathematician, he's mathematically oriented. So he asked me, like, what is n equals 0? So what if you have a bracket n? What if we say that n equals 0? What's that? Like, how do you get away from doing these kind of like general like things? What if it's 0? What if it's 1? And the thing that I wanted to say that I did was that n is supposed to represent points on circles. So n equals 0, then you're pretty much saying there's no point on your circle. So, you know, where does that take you? That's not pretty far, is it? So n equals 0, no point on circle. N equals 1 is 1 point on circle. N equals 2 is 2 points on circle. And further, we're also like using this little bracket thing to do some mod, right? So again, we're doing reviews. We're reviewing back because, you know, I don't know who's watching or what's watching. But pretty much we're putting whatever n is inside of the bracket of this mod. By the way, I bought some new markers, some new colors, so kudos for that. So mod n is pretty much like what's happening. I don't know if you guys can see that pretty well. So mod n, right? So I don't know if you know about mod, but pretty much what happens is if you put a number into mod, then that's as much as you count. So if we say mod 2, let's just say that we say mod 2, that's what happens. That means that if we're counting up, if we're going like from 0, well, we can actually use a circle here that I have written. This is going to be like point 0 and 1. I'll rewrite this. So this is the case for n2. So we're saying here that I realized watching the recordings that I have this tick to touch my nose with my fingers. I don't know why. And I only do this when I'm recording too. Well, maybe. Maybe I only realize it when I'm recording, right? Mod 2, that means that if we have these two labels, we can't get further from 2. So if we're adding numbers, if we go like, 1 plus 1, that's going to be 0. Because we're saying that from 1, we're going 1 point over. So we get to 0. If we say 0 plus 1, of course that's 1, right? 0 goes to 1. But what if we say 1 plus 2? What's that going to be equal? Well, we'll start at 1. We go then 1. So 1 plus 2 is 1. Because it goes 2 points. So it sort of like comes back around. Or if we say 0 plus 3, that's also going to be 1. But it goes like 1, 2, 3. So it's 1. The reasoning behind all this is that however how many numbers you go over mod is whatever you get as a result. So in this case, we're going for the 3, so how much is 3 over 1? Well, actually that's 0 times 2, so these two are the same kind of operation, really. Same result. Because in the usual way, this is 3, right? But 3 is one number over mod. So that means that we take away whatever mod is and put the remainder on it. But it has to be like a multiple of it, because if we, let's scale this up. I know we've seen this before. If you know this, it might seem boring, but I've just been realizing that a lot of people sort of like watch these as they come out. So what are you gonna do? And all right, let's go for mod 5. The usual example I do is mod 8, but let's do mod 5. No, the example we did last time was mod 5. Let's do mod 8 then. It's the example I put on the Discord server today. So I talked about this. We use several colors of this thing. So I'm going to write in here. I'm not even going to write an octagon because technically that's not even like there yet. So I'm going to write 8 points that are supposed to be equidistant from each other. So that means that they're inside of an invisible circle. So they're inside of a circle. I'm going to use even another color for this. So these points are inside of an imaginary circle. And these points are all the same distance from each other. And because, well, this is a pretty badly drawn circle. Maybe I should start with the circle, right? Start with the circle then. Sorry for all these rewrites. So let's say we start with a circle. And then from there, we say that there's going to be 8 points. So 1 point, 2, 3, 4, 5, 6, 7, and 8. So we have there are 8 points. And we're going to label them. We're going to start with 1. 1, 2, 3, 4, 5, 6, 7. Mod 8, we can't get to 8. 8 is 0. So this would be, in turn, like that. Well, actually, this would be 8. Right. So now we jump into what K is, right? So we talked about this before. The K is stepping, right? K is stepping. So whatever K is whatever we add on the cycle until it closes again. So we're going to do a little math here, which I think is a little fun. We're going to start counting at 1. So I'm going to write here 1 plus, and whatever I come up with K is going to be here with my black number here. So actually I should use another color. Do I have more colors? I have here this green color. So this is going to be my K. So here I'm going to write in 2. Maybe I should write in 1 first. So 1 plus 1 equals 2, and then we're going to jump in here to 2 plus 1 equals 3. 3 plus 1 equals 4. 4 plus 1 equals 5. 5 plus 1 equals 6. 6 plus 1 equals 7. 7 plus 1 equals 0. There's no 8. And finally, 0 plus 1 equals 1. And so you see how now we're starting from where we started from. We're ending from where we started from. So what's happened here, we went from 1 to 2, from 2 to 3, from 3 to 4, from 4 to 5, from 5 to 6, So we've inscribed an octagon. So we could write this, sorry about this guys, could write this as this, 8 over 1. This is not clear at all. But because 8 over 1, we write it over here, 8 over 1 is equal to 8, we simply write A over 1 as just 8. So whenever we have a brackets and that number inside, we take for granted that that's a polygon. We talked about this before, right? We're going to do this one more time with this like mod thing. I'm trying to keep it simple because again, I realize that kids watch this, man. So what are you going to do? Alright. So now we're going to write in 8/2. Okay? So we're going to start at 1 again. Actually, we can maybe start at 0. I'll start at 0 this time. So maybe I have to change up this color, right? So 0 plus 2, that's 2. Then we started at the last number we got, that's where we start, right? Pre-Fibonacci like sequence, I guess? Nah, not really. So 2 plus 2. And so 4, we start over here, 4 plus 2, that's a 6. 6 plus 2, that's a 0. That's the number we started with. So if we write that down over here, we start, I'm going to use here now the red, because why not? I'm going to go 0, we say the 2, 0 to 4, 4 to 6, and 6 to 0. We have your little sequence and it closes, yeah? So we're gonna, we realize there's some numbers missing in our sequence. So now we're gonna start counting at 1. So now second system, so this is like a closed system. So this is closed, right? Now we're gonna start at 1 over here. So 1 plus 2, that's 3. 3 plus 2, that's a 5. 5 plus 2, that's a 7. And 7 plus 2, that's a 1. So we start at 1. Yeah. So 1, 3, 5, 7, and 1. And so we have here another closed system. And there are no points left. All the points from 0 to 8 are all accounted for. We have 0, 1, 2, 3, 4, 5, 6, and 7, and 0. All the numbers are here. So the system are closed and we get two sets of things, two figures. So it just so happens that if k and n are common, so I remind you that this comes in the form of n/k. This is a star polygon form. n/k. N is this, it's how many points, it's the mod, it's how many points on the circle, and k is what we add to jump around it. So we get some sort of system by just keeping this number as a constant. It's just a constant that keeps adding. Or subtracting, we could get the same thing by subtracting. We start at 0, we subtract 2, we end up at 6. 6 minus 2, 4, 4 minus 2, 2, 2 minus 2, 0. Works the same way backwards as forwards. So k, in a way, it's a plus minus kind of situation. I want to have you notice, though, the amount of sets that we have is the number of k. This happens when k and n have a common factor. So I'm going to erase this a little bit. Maybe I should write it over there, right? So if n and k have a common factor, we will have what the fuck? We have k amount of, I'm gonna say polygons. We have k amounts of polygons. So if n and k have a common factor, we have k amounts of polygons. 2 and 8 have a common factor of 2. So what we do in order to express this same shape is we write the denominator, the k number, and we take it outside of the fraction. So we write the 2 now outside, and we sort of just divide whatever 8 over 2 is. We write that inside of the bracket. So 2 over 8 is 4. How many times does 2 fit in 8? 4 times. And I should write this with a deeper color, no? So 8 over 2 is equal to 2, 4. 2 squares. And we see clearly here we have 2 squares where this 8, 2 is just like that sequence, this sequence of sets. And we have here that's 2 squares. So pretty much by looking at the star polygon at the nk and taking this into account, we might know when it's a compound. This is a compound star polygon. When k and n are not common factors, when there's no common factor between k and n, then we call that a star polygon. No compound, just star polygon. This is a compound star polygon. Alright, so we're getting somewhere, I can dig it. Last example. And we're going to see here how... Alright, so we saw the 8-1 and we get pretty much the polygon itself, right? The octagon. We saw here the 8-2 is made up of 2 squares, right on. So last one is the 8-3. Like that. So 8 and 3 do not have a common factor. We're going to start counting at 0. See if I can do this fucking combo thing. So 0 plus 3, 3, 3 plus 3, 6. 6 plus 3, that's 9 in it. But because we're in mod 8, how much are we going over 9? Over 8? 1. So 6 plus 3 is 1. 1 plus 3, 4. 4 plus 3, 7. 7 plus 3. Again, 7 plus 3, that's 10. How much does it go over 8? 2. Again, this is all mod 8. Mod 8. So 2 plus 3. It's 5. And then finally 5 plus 3 equals 8. 8 is 0. And we're back to where we started from. So this is a closed system. And then you see there's no overlap. So here I'm going to write this one in blue. We start at 0, from 0 to 3, from 3 to 6, from 6 to 1, from 6 to 4, from 1 to 4. So we're just going to follow this. So start from 0, go to 3, from 3 to 6, from 6 to 1, 1 to 4, 4 to 7, 7 to 2, 2 to 5, 5, 0. And so we have here the 8, 3. That is this star polygon inside. We saw last class how the extension produced like all the star polygons in itself, right? So we saw that already, but just to be clear how the difference between a compound star polygon and a simple, not simple, but just a unicursal star polygon. These are unicursal. You can get, without lifting the pen from the paper, you can complete this system. Whenever they're not common factors, when they are common factors, compound. Pretty fast, pretty cool, right? Then of course we saw the internal angle formula that works. We're not going to see that pretty much right now, but we are going to move on to the minimal triangle formula. I forgot what time I started this thing, so I don't know how much I have done so far, but we'll see. All right, so I'm going to draw another octagon this time. Like that. And I'm going to distinguish between, so I have to make sure that first of all, there should be a clear center. It's a center. All the lines go through it. So some lines are going to be radius, like that. And then the other lines are the apothems. There you go, from the midpoint of the edge to the other midpoint of the edge. Well, that happens in even numbers. In odd numbers, this thing just becomes a radius after it crosses the center. So we should do a little anatomy of shapes right now, which is long overdue. This point right here, that's a vertex. Right? That's the center. Maybe I shouldn't even call it that, but that's, pretty much, that's a center. We know that. So vertex, this is the edge right there. So whatever this thing is right there, that's the edge. This red line from the center to the vertex, so line center to vertex, that's called the radius. Line center to midpoint, which is this one, from center to the midpoint of the edge. Well, I should say midpoint of edge, right? Line center to the midpoint of edge, we call that the apothem. So we have the radius, we have the apothem, we have the edges, we have the vertices, that's what we call them in plural. Singular, it's vertex, right? Apothem. Radius in plural is radii. We have the radii, the vertices, the edges, and the apothems. Right on. All right, cool. Now, you might notice there's a really cool thing about these shapes. And one of the more striking things, is that this thing right there, the apothem, comes at a right angle on the edge. So that's pretty much like what distinguishes it, what sets it apart. That should be in black, actually. I like that to be in black. So we call this, if we had a pattern, if we had this line pattern, I don't have anything of the sort on the walls right now. I could pull one up maybe. But the point is that inside of this minimal triangle, we call this a minimal triangle. This little triangle here. Because this is mirrored, and then this thing is just arrayed around the center. So this bit is what would make this pattern be complete if this pattern was radially inclined and inside of this octagon. So this triangle, which maybe I should select somehow. Actually, I'm going to move to my right over here. So we have here sort of like what makes this. Maybe I should write also like what that is. We have the edge. Let's call the radius. That line right there, the black line, the red line, and then the green line. That's the apothem. And what we have here, the edge. And that's the midpoint. So some anatomy there, right? You have this sort of, this condition. Now what I want to do is I want to focus on this triangle, because there's actually a very beautiful way of looking at this triangle. Alright, so just a little recap. We've said we're using radians for all this thing, right? Remember radians? We're using pi. So pi is half a circle. Like that. So pi is that pretty much. Like that's pi. That's the angle of half a circle is pi. So the full circle, the full turn, this is 2 pi. It goes twice around the circle. Twice around half the circle. So half turn, full turn, 2 pi. Yeah, sort of? Alright. So the thing is that any point could be turned into a circle. We have a center here, and so we have a circle right there. And we could center our circle on the center of the octagon. So what happens is that if we have this, we could say that this division on the radius, these two red lines, I should draw that over here. So we have this circle, we have this center, and then we're going to focus only on the red lines that are happening there. So these kind of go like that. So we're imagining that there's no green lines, so we see only the red lines. So if we say that a full circle is 2 pi, and we have this split into 2, into 8, then this angle right there, that's going to be 2 pi over 8. So if we include the apothem line, those green lines go right in the middle of it. We shouldn't use black for this. Yeah, sorry. The green lines go right between them. And so we are dividing now in half. So this angle, what the hell? Dude, there's so many cards now. Yeah, well, my bad. But this angle right there, this thing, would be pi over 8. That angle right there, that's pi over 8. And further, we know that as long as your triangle is flat, as long as you're in flat land, in the flat world, there's 3 worlds, by the way. I haven't talked about this at all, but there's 3 worlds. 3 worlds of geometry. There's the flat world, the spherical world, and the hyperbolic world. And what triangles are in each world is what sets them apart. Flat triangles add up exactly to pi. That's one of their things. Spherical triangles look a little fatter, like that, and they equal to more than pi. And these are all projections, by the way. And hyperbolic triangles look like that, like a little saddle, and they are less than pi. So pi has just a very beautiful way of just connecting the different geometrical worlds. So everything that I'm teaching you right now has to do with this world, the flat world, where triangles are equal to pi. We're not dealing with spherical, we're not dealing with hyperbolic, we're dealing with flatness. Flatness is the world of the ideal, the world of the shadow. There's no real conjecture. Not a conjecture, there's no analog. Like the closest thing we have to flatness in the real world is like minerals. Everything is curved, everything has curve, everything just moves in a curved way. But as long as we're flat, we can think of shadows, right? If I put my hand here and see the shadow is cast upon the surface. And so that shadow is what we study. In the world of shadows, we worry about this. So, okay, a flat triangle is equal to pi. All right, beautiful. All right, we have one of those such angles. Where should I write this thing? Let's write it here. So that angle right here, we're saying it's that one, and we're saying that this one is pi. over 8. This is a right angle. And so a right angle is half of pi. A right angle comes in like that. And so if pi is of a half turn, half of it is going to be half of pi. So a right angle right there is going to be half of pi. So what's half of 8? That's a 4. So it's 4 pi over 8. So we simply add 1 plus 4, that's 5. And so the remainder has to add up to whatever's missing for it to be 8. So 1 plus 4, that's 5. 8 minus 5 is 3. So that this angle right here is going to be 3 pi over 8. So this minimal triangle has these characteristics. And there's actually sort of a general way that we can state this. We only need to be aware that whatever polygon we're working with, this one will always be 1, this one will always be half of whatever the number of sides it has, and this will be the remainder, the difference of those two. The difference of the sum with the, alright, let's just write it down mathematically. And yeah, I mean, it's cool, isn't it? Let me erase this. So let's go for a general. What general rule could we extract from that? So this right angle has to be half. This one will always be 1. Or rather, it will always be like pi over n. So whatever sides you have, it's going to be pi over that many number of sides it has. And this one over here will always be half of n. So it would be like n over 2 times pi over n. This is this angle, pi over n is that angle, and then this angle is going to be the difference of these two. So we're going to subtract this from this. So it's almost like we're going to write it now n over 2 minus 1 times pi over n. And so by using these numbers, we just have to like plug in how many sides our figure, our polygon has, and we get the minimal triangle. Alright, so we got the minimal triangle. What next, Einstein? Alright, well, we can use the minimal triangle to construct many polygons, and from there, like, construct circle packings and rhombi. I did mention that I was going to see one more thing though. But yeah, so this is pretty interesting, this is pretty cool. Some anatomy for you. It's a formula to get a right triangle inside of the polygon. I think that's dope. That's cool. We can, like, you know, get some other figures on it and whatnot. It's interesting. But yeah, so this is about geometric patterns in Islamic geometry. So in Islamic geometric patterns, so we have to like jump back into a pattern and sort of analyze it for what it is, right? Oh, that's right, I remember now what we were going to see. So I just wanted to go over the formula, but now this is very important for folding the Islamic patterns. This comes in mighty handy. And so I will need to actually write an octagon again, won't I? Can we get away with not? Well, the octagon is just a very cool example, so it doesn't hurt to rewrite it. I don't know why I get so itchy. I guess because when I'm teaching, I keep my hair on my face. I don't know why, and so it makes me itchy. And so okay, so we're gonna go towards the center there. We're gonna write in the apothem as well. Nope. We'll start over. By the way, please let me know what you think of these things. Like, I don't know why. I know I do them because I get this positive feedback from certain people. And some of you watch it. And I hope that this helps you learn or at least appreciate geometry in another light. I met a lot of people who are like traumatized by math. They don't like math. They think it's boring, or they think it's useless, or they think that they're just not up to it. But I think that math looked right can be quite beautiful and exciting. So this is a great way to like do that. At least for me, this is how it went. I have here an octagon again, inscribe my apothems and my radii. But now I'm not going to really worry about the minimal triangle so much. What I am going to worry about are the stars. So I'm going to write here my 8/1 first off. It's the polygon itself. 8-2, and the 8-3. These are my three stars we've seen so much. K, of course, we saw that last time, but I should write it here. K has a constraint that it has to be less than half of n. It's a constraint we saw, but this is the only constraint that really matters. K has to be less than half of n. Otherwise, it don't work. Otherwise, it's just a flat line, and after that, it repeats. So we get only these three numbers that we can use. All right. So the thing I want to sort of show you, which I think is rather incredible, is that there's a relationship between what star you're using and what line there's going to be a perpendicular line towards. So I'm going to write in my stars on my on the radii. This is going to work also on the apothem, but I'm going to write my star on the radii. I'm going to start with the 8-2. Should I use another color? Yeah, I'm going to use blue. Just to distinguish each, and then I'm going to use some other color for the 8-3. So 8-2, we're going to start here. And go up. Well, let's just focus on that because we could complete the system, but let's just focus on that. It just so happens that this line is perpendicular to this one. All right, what is that one? Well, it's the first radius. So it starts at radius and then on a radius. So I'm going to write in with some red here to distinguish that this line, this 8-2, is perpendicular to the radius as well. And then I'm going to write here on the other line, I'm going to write here the 8-2. The 8-3, but I'm going to go this way. Instead of going that way, I'm going to go up just to, visually distinguish them. So from here, I'm going to go this way, 0, 1, 2, 3. You're going to see that this one is perpendicular to this one. So this one right here is perpendicular to the green, the apothem. What I want you to note is that we're starting drawing on the radius. If we started drawing our star on the apothem, it would change the whole thing. But what's important is that if it's odd, it changes. If it's even, it remains. So if you're drawing your star on the radial line, on the radius, on the vertice, then it's going to stay as a perpendicular. Somebody's outside scrubbing. Yeah, okay, so odd numbers change. Odd numbers are, you can even see that with the 8-1. What's the 8-1 perpendicular to? You see that? So there's a sequence. And of course, we need a bigger star in order to see how this actually keeps going. But if we started our star, instead of the radii on the midpoint, you can see that right here. So I'm going to draw this one with what? I'm going to draw this one with a black. So same stars, but I'm going to start in the midpoint. So here I'm going to go toward that. So you're going to see how, and well, of course, this one actually would go also here. Because this one goes, this is the blue. Right? And so you see that when we start at the midpoint, we actually also have this thing where it changes. Now I want you to note that, well, maybe I should change these colors, right? Yeah, I should change these. Well, I don't want to change them so much as I want to just make sure that you understand that these are coming in and starting on the vertice. But when these come in and start on the midpoint, on these greens, so I'm going to write it over here. The 8-1 on the green is perpendicular to the red. And then the 8-2 on the green is perpendicular to the green. And then the 8-3 on the green is perpendicular to the red. So you see how they shift. So depending on where you're starting, if you're starting on the vertice or you're starting on the midpoint drawing your star, it's going to be this sort of a back and forth thing. So if you know that your K is odd, so maybe I should write that here. So when k is even, the line is, this is a perpendicular sign, the line is perpendicular to what? The line that it originates from, the point that it originates from, the radial that makes contact to the point. How would you write it? Because if it's, this red is the vertex, and this green is the midpoint of the edge. So it really depends on it, but the thing is that no matter where you start, it's going to change. So if it's odd, it'll change from where it starts. So here k is 1, and this is red, so it changes to green. Here k is 2, and this is red, so it stays in red. K is 3, that's odd, goes in red, goes to green. So if you can distinguish, the point of all this thing is, if you can distinguish between which one of these radial lines you're working with, you know where you have to be perpendicular towards. And the thing about, well, maybe I should finish writing that. When k is even, the line is perpendicular to what? The radial line that spawns it, the radial line in contact with the point? Yeah. To the radial line type. Because there's two types, right? There's the apothem and there's radius. Is to the radial line type in contact. Yeah. I guess I don't know how to say this. This one is badly worded. It's even. It's perpendicular to the radial line type in contact with k. With k, I guess. Yeah, and when it's odd, it'll change. And the line is the radial type in contact with k. To the opposite, I guess. And when it's odd, it'll, yeah. When it's odd, it won't. When k is odd, it reverses, inverses, I don't know. I'm gonna write inverses. Again, I need your suggestion for this, guys. If you're actually watching along, it'd be great if I had your suggestions. But again, so I think this is pretty cool. I had to sneeze. And yeah, so odd numbers and even numbers have this thing. So I want to show you. Might as well show you, right? So much talking. Too much talking, too much conversation. All right. So I don't know if you can see this. You probably can't, right? This is such a small little piece of paper. And I dropped it. Yeah. By the way, if you want to know how to fold this one, hit me up. That one is there's a video of it on my YouTube channel. But you know, if you want to see it. Also, this one's on the YouTube channel. If you want to check that one out, it's a fun little thing. We haven't got into that yet. But yeah, so this is really all about what we say it is about. I don't know, dude. I'm just gonna fold an 8-fold division on this square thing, like pretty much like this, but on this little square. And I'm gonna. Actually, I don't have to. What I need to show you is how easy it is to fold a perpendicular line. That's the point right now. So with folding, if you want to fold a perpendicular line, all you have to do is make that line fall. So for instance, here I could fold a line, any line. I'm just gonna write it down here with a pen. Don't make it messier, but whatever. Drop that. I don't have any other. Where are the others? So there's that line. If I fold this line onto itself, anyway, and then there. So this line that I just folded, where the line falls on itself, these two lines are perpendicular. This is so badly drawn, but that's true. I mean, that's just a thing about origami. You look at the axioms. So when you fold the line onto itself, the resulting fold will be perpendicular. So if you have a point of contact, and you know which one of this type is going to be, just by knowing what k is, just by knowing if it's odd or even, you can know which line you're going to have to be perpendicular towards. So I think that this little rule works great for folding because how easy it is to get a perpendicular line by folding. So I think that this is gold right here. If you want to fold Islamic patterns, this thing is gold. It really helped me out. Again, this one was discovered about a year ago by yours truly. And yeah, hold the applause, hold the applause. As long as I don't publish this, I think it's still like in the air. But I have to publish it eventually, and it's math, and it's science, and it's cool, and it's folding, and it's art, and it's math, and it's all great, it's all there. And I really should maybe get a haircut. Maybe not, I just, it's a bad hair day today. It's a bad hair day whenever I choose to do these. And I think I'll leave it there for now. What time is it? It's 4:57. Well, I think we got time for an exercise, actually. If you want to join along with an exercise, I'll activate the comments and we'll do a little exercise over here on the table. So join me. Oof, we got nobody today, huh? I don't know, let's just cut it. Let's just cut it because, yeah, don't feel comfortable doing this by myself. Anyway, guys, take care, enjoy, and we'll see you next time.